An analog-to-digital converter, or ADC in short, is one of the critical peripherals required to build cost-effective connected sensor networks. An accurate, on-chip ADC can save BOM cost by offering precise measurement of analog sensor data without the need to include an expensive external ADC to your design. Due to the intricate design characteristics of an ADC implementation in silicon, it takes much expertise to get it right, especially on systems where there are complex, on-chip analog peripherals like RF radios. The WFI32 device family comes with a power-packed 12-bit 2 Msps dual-core SAR ADC with up to 20 analog input channels. Even when paired with the on-chip 2.4 GHz 802.11 radio, this ADC showcases excellent, industry-leading performance. We measure ADC performance using parameters like INL and DNL linearity and code density, among others. Without a precise design, the transfer function cannot be linear. The variations are even more with a change in operating temperature. Let us take a quick look at some of these characteristics of WFI32 in comparison to other, similar devices in the same market space. One representation of overall accuracy is the gain error. To calculate the gain error, we feed in a known voltage to the ADC and compare the reported ADC reading to the expected value. As you can see here, the gain error of WFI32 lies within negative 0.3% to plus 0.7% over temperature. To visualize this specification more straightforwardly, we can plot the reported output voltage for a linear ramp input. As you can see here, the reported output follows the input across the temperature very closely. What you see here is the best-in-class performance of WFI32. The results of other devices in the market with similar spec and functionality is not even comparable. As you can see here, the percentage error in other devices in the market ranges between negative 2.14% and 2.97% across the spec temperature range. The error also varies from device to device, which makes it difficult to compensate in software. Another test used to compare the ADC performance between two similar devices is a code density test with a linear ramp input. It is also popularly known as the histogram test. This method involves collecting many digitized samples over a period for a well-defined input signal with a known probability density function, or PDF. Once samples are collected, we perform a statistical analysis of the data. If the ADC has no INL or DNL errors, all the conversion codes have an equal probability of occurrence when a linear signal is fed to the ADC input. This signal is typically generated using high-end, professional ADC characterization equipment. However, we can use benchtop equipment for a quick comparison. This video uses an OpenScope MZ from Digilent as a USB function generator to generate a sawtooth wave. We fed this 3.3-volt low-frequency linear ramp input to the ADC of the WFI32 and another device with similar functionality and specifications. Once the ADC conversion data is processed, we can visualize the code distribution function using a histogram. As you can see, the histogram of similar devices from other vendors are distributed unevenly. In comparison, the code distribution of WFI32 is highly linear with an even distribution. This means that the ADC of device E generates different output codes for a given input voltage when sampled at different points of time. In comparison, the WFI32 ADC has a very small variance in this situation. This video used easily accessible benchtop equipment to make a quick comparison of the ADC performance. Stay tuned for part 2 of this video, where we perform this comparison using professional lab equipment. For more information about WFI32, please visit the Microchip website or contact your local sales representative.